This is lecture 4 for the additive manufacturing class. I apologize, I've been having a lot of issues with regarding creating these lectures and posting them and things like that, and I hope that I'll be able to do this. I plan to upload all these lectures on a YouTube channel that is specific to this class or me, so you can look at them anywhere and on any kind of platform. That's what I'm really hoping for. But unfortunately, sometimes loading these takes a long time. I mean, even 500 megabyte files takes about 3 to 4 hours to do that. So each lecture, creating each lecture takes me about 7 to 8 hours. And if there are any kind of um, stoppages and things like that, there is no way for me to stop it, pause it, and start all over again. So I have to start it all over again, which is what has been really been happening. But in any case, going forward, this is regarding additive manufacturing lecture 4. And in the last class, we talked about CAD modeling and what are some of the issues with the modeling approaches and how it is resolved in the actual build process. And in the current lecture, we will talk a little bit about road mapping. And why I want you to understand about road mapping is because road mapping is how we can figure out what is the current status of this technology and how it is going to be taken forward in the future for the different industries in particular. And just to bring to your attention, the most useful additive manufacturing processes have particularly focused on metal parts. They have not yet become popular with polymers or polymer composites, but I'm hoping that this will be taken up in the near future, maybe in the next 1 or 2 years or so. And the details of many of these are drawn from a NIST workshop in December 2012. There have been follow-ups with that, but I think this really tells you those things. In any case, um, the what is a technology roadmap? What is the definition of a technology roadmap? It's a plan that matches short-term and long-term goals with specific technology requirements to help meet those goals. And it is typically done for any new product or process or for an emerging technology. How this happens is people who are working in this field from different organizations, they get together and help to reach a consensus about what are the needs and what are the technologies required to satisfy those needs. And it helps us to forecast how we will meet those technology developments. And it provides a framework to create that. So people know what exactly they need to do in order to take this technology to the next step. So typically this is a schematic. So you look at um, what are the preliminary steps required, then how do we figure out? So most of the time what happens is that the organizations working in this area, they would get together and say, hey, I will do this, I will focus on this, you focus on this. So, and then after a couple of years, we will come back together and look at what has been done and what further needs to be done and what are the challenges and so on. So we talk about what is the follow-up required to do that. So this one, like different things, like, for example, in additive manufacturing, we looked at multiple technologies. So each of them, we talk about what are the performances, where exactly they are, and what is the future and what is the time scale. So this is a very broad brush type of a thing, but it helps us to understand what needs to be done. So, in additive manufacturing, the very first roadmap was done in 1994. And it was done by a working group at the Department of Energy. And in those days, it used to be called rapid prototyping. If it were the industry based technologies, then the solid freeform fabrication was a terminology that was used primarily by academic institutions and funding agencies. And what kind of techniques need to be done, and people try to add product design and visualization and high-speed machining. And remember that in the early 90s to mid 90s to late 90s, still we were at the mercy of many of these machine manufacturing companies, because the interfacing software used to be very specific to that machine, and you could not create a design on one platform and easily transfer that to the interfacing software, so that, I mean, they would not understand. Or, even if they could partially convert that, there would still be gaps in it. So the for component that you designed using, say, the fuse deposition modeling, would not be compatible with the machines that were using laser sintering. So then, you end up with layers that are missing or rods that are missing and things like that. So you ended up with a part that was not perfect. So that's why the road mapping exercise was extremely important. So in 1998, they had a follow-on roadmap that was following the 1994 roadmap, and it added an industry perspective with a focus on rapid prototyping and additive manufacturing. And remember that the industry was driving this, the industry using these technologies was driving this. So it was a better roadmap than the one made in 1994. And they predicted what the future could be. And they said that direct manufacturing systems. So the gold standard is always that you can't make parts, you can't make additively manufactured parts that would just be for form and fit. You have to make parts that can be used directly in a particular application. So multiple things, they talked about all that. And of course, I mean, we all want things that are inexpensive and cheap and disposable types of materials and things like that, recyclable materials and things like that. But again, it wasn't the perfect roadmap, but we thought, by 2010 or so, and people kind of understood that by 2010 or so, most of the patents that were originally acquired by these companies, the earlier companies, would all be expiring. So there would be a rapid transition to things that were cheaper and faster and things like that. But what they did not take into account is that there were a number of, I mean, these companies, they started hoarding this money, whatever income that they had, and they started buying up new technologies, or buying up or creating new patents, new follow-on patents to the earlier patents. So again, till the patent office started saying that, hey, you need to have patents that are based on, I mean, the people who came up with the idea first. It's not just um, who will patent it first. So there are some changes in the patenting laws that have taken place in the last couple of years. So that has really helped and accelerated the innovation in this technology realm. Okay, there was a it took something like 11 more years because people were so busy trying to create new technologies and things like that. So in 2009 they had roadmap number 3, and what they found is that in 1998 most of the players in the road mapping exercise were the uh, companies and the customers. In 2009, there was a lot more participation from academia and the funding agencies. So I think it was a better roadmap than the one in 1998. So the headlines are that you can create a research agenda and you can see what exactly needs to be done. And I don't know how much of you know about the what is called the Small Business Innovative Research Program, or the SBIR program, that is funded by the federal government, 11 agencies, and there is also Small Business Technology Transfer Program to transition university funded research into commercial products. So that is called the STTR program. So there are only 7 agencies that do that. But what has happened is that in the last maybe like 3 years or so, if you looked at the topics, that research topics that are coming out in those solicitations, there are a lot more additive manufacturing related solicitations that are coming out. And you can, I mean, if any of you are interested, you should go and look up the topics that are part of this SBIR, especially the Department of Defense type of programs. You can find that there is a lot more emphasis on additive manufacturing and how you can transition this technology into the real marketplace. So the road mapping exercise is supposed to give us that kind of an idea. So what are some of the common themes of additive manufacturing according to these road mapping exercises? What do we need? And these are, you can say that these are broad across the whole technology realm, which is that first of all, you need consistency and repeatability. The idea is that if you want consistency, say for example, if you can say that these are my properties with 95% confidence level, plus or minus 1 sigma or 2 sigma or 3 sigma and so on. It needs to be repeatable and it needs to be consistent. And with additive manufacturing, it was never that case. Nobody really cared about those kinds of issues in the past. But now we are, because we are making parts for actual applications. So we are making functional parts rather than functional form and fit. So, and in additive manufacturing parlance, we call this, you make one part that gives you the consistency of 100,000 parts. So can you predict the properties of one part as soon as it comes out of the build envelope and say that if I make the 100 part using this technique, it will have a property that is within plus or minus 2 sigma with respect to the first part. Can you say that? We are not there yet, but that is the goal. And how do we make that happen? And so sensor technologies are going to be a big part of the future of additive manufacturing. How do you sense the properties? Non-contact, I mean, for example, if you make a machine part, how do you know what the properties are going to be unless you destructively test it? In additive manufacturing, you don't want to be testing 100,000 parts because to make those parts is going to be pretty expensive. So, how can you predict these properties in a non contact way, in a non destructive way, is the goal of the future. So, for that, you need to create process standards. You need to have sensors to give you closed back loop feedback. So if you make one layer and during that layering process, you find that, hey, there are some areas in this layer that is missing the material. So before the next layer is laid down on top of that layer, can you go back and repair that area before it moves on to the next layer? So in order to do that, you need to have closed back loop feedback. Then you need to be able to analyze the data and you need to be able to give that data for the modelers or the design engineers for their finite element modeling and so on. So you need to do that. And the big idea now is that we need to be able to generate material property without destructively testing 100 parts or 1,000 parts. So you don't have to be making witness samples to predict those kinds of properties. And in order to do that, we also need to be able to exploit the unique features of additive manufacturing. You know that in additive manufacturing, because of the way the material is laid down, you have properties that are better in one direction when compared to another one. So rather than saying that your anisotropy is a problem, can you take advantage of the anisotropy that is created in these parts? So using these, that will go directly into your design rules and tools. So for example, if you know that it is stronger in the X and Y direction, can you make that X and Y direction in the Z direction? Can you lay down the part such that the X and Y direction actually now becomes the Z direction so that your part becomes extremely strong? So, or if you have a robotic arm, so you first lay down the part in the X and Y direction, then the robotic arm comes and turns it over, and now the head goes and feeds the material on the Z direction so that you have better properties in the Z direction. Then it goes back and turns it back into the X and Y direction and so on. I don't know. I hope I'm making you guys understand what is going on here. So when you do this, you are creating a new set of design rules and tools for using additive manufactured parts for actual applications. And then you have to be able to inspect those parts for quality control. And how good has that quality control got to be? So tomorrow's and today's additive manufacturing technologies are going to be all based on sensing technologies, non-contact sensing technologies, laser-based technologies, kind of different kind of a technology than what it was originally meant to be. So if you are using a laser for laying down the part or sintering the part, can you use the same laser for actually sensing the part too? We don't know, but that's going to be the goal moving forward. And then we need to create a new set of engineers who understand about additive manufacturing, who can use this. See, most of the people, even people like me, we are kind of stuck in the old times. We believe, so we only remember not exactly the additive manufactured parts, we remember the subtractively manufactured parts, the machine parts. You make a huge part, you take a huge block of material and you hog out the material to create the final part. Tomorrow's engineers and the engineers that we create today have to start thinking differently. They have to think only in terms of how do we make this part using an additive manufacturing process. I hope that I am making you guys understand in the future this is going to be the case. No more old machining standards, no more old ways of making parts. It is all going to be additive manufactured parts. And for that, you need to be able to create what are called national testbed centers. So if somebody comes up with a new technology, somebody comes up with a new machine, they need to be able to send it to a national testbed center. There are people who would use them and figure out and tell the whole additive manufacturing community, hey, this is what this could be used for. These are the kinds of properties that you need, and these are the kinds of process models that you need for processing these materials. And then these are the kinds of properties that you can get if you make material A, material B, material C, material D, and so on. So can you make these machines that are compatible with different kinds of materials and different kinds of technologies and different kinds of industries? Can you do that? And for that, we need to create what is called a National Testbed Center. And NIST is already at the forefront of that, especially on the metal-based additive manufacturing, but there are going to be much more challenges going forward, say composites, and so on. And one of the National Innovation Centers now, the one that was created in, I believe it was created in Youngstown, Ohio, for composites. Uh, it is going to be uh, used for composites. The one in Tennessee is going to be used for making metals and so on. So there are going to be national innovation centers specifically related to different kinds of technologies. And that's going to be the path forward in the future. And this is all going to be transformational. I mean, these are not things that we really thought about in the future, in the past, but that's going to be the path forward in the future. And this is going to be helpful to create new types of high risk, high payoff research methodologies for this additive manufacturing in particular. And these are the types of organizations that was represented in the 2010 roadmap exercise, especially um, related to defense platforms. And so you can see that NAVAIR, for example, the 4.1, 4.3, etc., they are all the initial stages of the technology development exercise. When you go to 5.2, 6.7, I mean, those are the different offices that were related to that. So you can see that these are all the multiple agencies and multiple industries, multiple academia and things like that. And Oklahoma State University is not yet part of this, but we hope to be part of this in the future. So for the science and technology itself, these are the broad brush strokes of approaches. Um, what is the near-term requirements? Near-term requirements are validated predictive structure property processing models. What do I mean by that? For example, if you laid down a material, say for example tool steel, PH17 tool steel, okay? You did that and you used a certain speed for laying down the road and you made the part in so much time. Can you predict that the properties of this component after it comes out of this build envelope will be so and so with a certain amount of predictive capability? Can you do that? Right now, no. But that's going to be the near-term goal for the future. What is the long-term future? We need to be able to make alloys designed specifically for direct DDM means direct digital manufacturing. So again, a lot of acronyms and lot of terminology is being thrown about, um, you know, left and right. But that's going to be the future, and it's going to be a closed loop monitoring and fabrication of systems, and sensor data is going to be much more critical and important for controlling the process itself. So these are the multiple things for the near term, mid-term, as well as far-term types of challenges for the additive manufacturing technology. Again, multiple things. Um, what are the near-term requirements? What are the other near-term requirements that we should be looking at? Industry standards. So if you used additive manufacturing, say in the automotive industry, can those standards, those process models be used also for the aerospace industry? Can it also be used for um, the medical industry? Can it also be used for other industries? So if you have commonality between multiple industries, then it makes it much more useful. I won't go over too much in detail about all this, but one thing to note is that, again, I want to point out that because of the way the patents expired from those that were issued in the early 90s, now we have an explosion of low-cost 3D printers. And there is much more acceptance. I mean, like, high schools and middle schools and elementary schools are using these technologies for different things. And the the true significance of this will be felt once we start seeing that every household has a 3D printer that can make components, that can make parts that can be used in their day-to-day lives inexpensively. So can you create a $59 3D printer that can be used by household, I mean, by a student in a house to make, say, um, a door handle that was broken. So you make the part, and then by the time you come back in the evening, it is done. Can you do that? Right now, no, but it can be done. So, or you can go to a local Kinko's and build this part and take it, and just like you go to Kinko's for copying, can you do that? Right now, no. But this is the midterm goal for according to the 2010 roadmap. Going back to parts that are much more engineering relevant. I mean, plastics and uh, paper and wood and things like that are good for the households and the common person. But what does the industry need? Industry needs metal parts that can be built by additive manufacturing. So for that, you need to be able to have extremely good metallurgical knowledge on the material properties of the powder and wire. So more powders need to be prepared and need to be done. So if you buy stock, I would advise you to buy stock in companies that are making metal powders, because those companies are going to grow a lot more in the future. Then once you know that, you need to be able to predict you need to be able to create a materials database, not only for the companies making the powders but also the industry. So, and this database and standards need to be shared with a lot more companies and a lot more people using this technology. And we need to be able to produce materials by design that have properties specific to application. So if you know that these are the properties that you require, then you need to be able to choose a set of process conditions that will give you those properties. I hope I'm making you guys understand, but that's going to be the goal of the future. So these are the challenges right now. There is no in situ monitoring, analysis, and feedback regarding material properties, distortions, etc. during the manufacturing process. So there is a barrier in measurement, but I think those properties, those challenges are slowly being met, and there is also a lack of understanding of post-processing issues regarding what kind of properties that you can get with respect to what kind of processing conditions that you have used. So if you make a part, is there some way for you to put in there, hey, these were the process conditions that were used for making this part? So if you have an ISO 9100 system for the quality control and manufacturing, can you take that information and send it along as what is called a traveler? It travels, the data travels with your part before it is assembled into your actual application. And in case that part fails, can you go back and look at, hey, these were the conditions that were used. These were not the right conditions to have used, because this is what it should have resulted in, which is why this part did not last as long as we expected it to. So these are some of the challenges. Everybody knows that. But I think it's not just the challenges, but we also need to know how do we overcome those challenges. And because many of these processes use heat as a means of depositing and as a means of joining those different parts of the part and the powders together, there is going to be a lot more effect of residual stress that is created in these parts. So which means that there is a huge requirement for post-processing, and you need to be able to integrate all that information into the manufacturing of this part. So till now, when you make these parts, it is all going to be, hey, it's kind of there is a lot of hand waving going on here. So you say, hey, I will approximately use this, and these are the kind of approximate properties that you get. And let's see if this will work in this application or not. But is that the right way to do it? Is difficult to figure out. Again, there is a lot of writing here. I apologize. So again, I'm not going to go over each and every one of them, but these are all I would like you to just go over that and make sure that I want you all to become champions for this technology. I mean, more than anything else, this is one of the reasons why I want to teach this class. I really I'm really fascinated by this technology. And I hope that all of you get the feeling that, hey, the opportunities for this technology are unbelievable. And this is going to be the wave of the future. I mean, of course, this wave has been going on for the last 20 years, but we have not, we have only scratched the surface. There is a lot more to be done and a lot more to be learned. And I want you to use this class just to learn. I mean, not just to write it on your resume, but just to learn from this technology. Again, sensing and controlling of the manufacturing process and the material properties is the biggest challenge, according to me. And then you need to be able to take all that and use it in your modeling and design tools. So it is not enough to just make these parts, but somebody needs to be able to take these parts or take the material properties and use them in designing components. So that is the only way additive manufacturing is going to be used by more and more industries in the future. So again, the processes and equipments, again, sensors dominated in this road mapping exercise. Um, Again, you can see that sensors dominated there. And process repeatability and reliability is again a big challenge, especially for the qualification and certification. And you need to be able to say that, hey, if I get this particular powder today, it is going to be the same 10 years from now. These are the same properties that I will get. And so that once I make the final part, those part properties are going to be the same 10 years from now what I made today. And these standards need to be a single one. So every industry needs to be able to do that. I mean, there could be some changes here and there from industry to industry. I mean, the automotive industry, when if they are using a particular alloy, they may not like to share the properties of that particular alloy, especially if they have developed it in-house. They may not like to share that with the rest of the world because it might take away their competitive advantage. But still, at least it needs to be able to be shared inside the organization. So there needs to be standardization, validation, and so on. So lot of challenges, lot of capabilities, lot of wonderful technologies, but still lot more challenges to be overcome. So I'm not going to go over every one of them. So in order to do this, what did they do? They figured out that the only way to overcome these challenges is by making different industries and different people make these parts under the same conditions, and then they do testing, destructive testing, and it is called round robin testing, which is a learning experience for all, and it helps us to identify what we don't know. So again, I mean, these are for modeling and simulation, the challenges and goals. Again, I am not going to go over every one of them, so I will let you guys read through that. So this is in one slide. These are the different things: process equipment, qualification, certification, modeling and simulation, and actually the materials. These are the challenges for additive manufacturing according to NIST. So this is an important reference. I would like you to please go over that, and I would like you to understand what are the types of um challenges for these materials and processes. And particularly, I think that this has resulted in what is called a democratization, which means that it has spread. I mean, in the early 90s to mid 90s, only those organizations which could which would spend $1 million plus could make these parts, could use these technologies. So there were a lot less number of people working in these technologies. But what has happened now is that a lot more people are using it because equipment has become extremely cheap, processes have become extremely easy to understand, and it has become very easy to teach people and make them appreciate what this technology is all about. Okay, see, for example, you yourself, did you guys think that you are going to be learning about additive manufacturing? But you took that, and I really appreciate your willingness to learn uh, this new old technology. And the other interesting thing is that if you go to Kickstarter, you will see that a lot of people are throwing up ideas in Kickstarter and trying to generate the initial source of funding for these processes and materials. And I would also advise you to go and look at the recent SBIR solicitation from the Department of Defense. See the number of topics listed under additive manufacturing. Can I please, I have not listed this here, but can I please ask you to go do that and give me and send me a one sentence answer. How many solicitation topics did you find in the recent SBIR solicitation from Department of Defense? This ended on February 8th, if I'm not mistaken. Can you please look there, go there, and look up the number of topics listed under additive manufacturing? You should be able to do that. Let me know what that number is. If I'm not mistaken, it is something like 50 or 60 out of something like 300 or 400 topics. So that's an unbelievable number. In the past, in the early 2000s and things like that, we would be lucky if we found 3 or 4 topics. Now it has become so vast. It has become ingrained in the culture of the world. Additive manufacturing has become so common. And so we need to be the champions for this technology in the future, going forward. So what are the industries that are going to be able to use these technologies? Every one of them, at the nano scale to micro scale to macro scale to large scale. So you have every industry that needs this technology, can use this technology at different levels. So depending upon the different scales, you have different challenges and different manufacturing approaches, and different processes that you can use. So this is, in a nutshell, what this is all about. So these are the different, this one actually comes from the ASTM standard, which I don't know why, but ASTM went ahead and canceled this standard for whatever reason. I have no idea. But this is what it is. And you can see that, again, this is a lot of information to gather and to accept in a very short time. And again, how has it changed design and things like that? And this is a timeline of how this has taken place over these years from 1986 onwards to 2014 at least. So 2016, 17, it has changed much more. And this is an important slide. These are the individual project numbers from National Science Foundation. You can see that in 2010 they funded 4, but you see these And these are the different kinds of areas in which National Science Foundation, which is one of the prime funding agencies in this country, has funded projects related to that. And you can see that the number of projects that they are funding in the control and process development are much more than in the past. So you can see that that is where all the eggs are going to be placed. So if you are interested in going forward and learning more about this, that's where I would advise you to go and learn about this. Okay. So anyway, I believe this is the last slide in this lecture, and I would be posting this to my YouTube channel. Okay.